Welcome to Math 2320, Section 4.3. In this section, we are looking at second order, homogeneous, constant, coefficient differential equations. So, the idea here is we're going to assume a solution of the form y equals e to the mx. What that generates for us is a quadratic equation that needs to be solved to figure out what are the proper exponents to be on our e to the mx. So in our first equation here, we do that. So I simply grab m squared minus m minus 30 is 0. And so factor it, and I figure out that m is 6 and minus 5. And so what I get here are two real roots. Remember that for a quadratic equation, there are three things that could happen. I get two distinct real roots. I can get one real root that's repeated, or two complex number roots. In this case, I get two real roots, and so my solution is of the form c1 e to the minus 5x plus c2 e to the 6x. All right, in question 2, we repeat the same process. M squared plus 10m plus 25 equals 0. That factors into m plus 5, m plus 5. So I get that m is minus 5. So I've got one real root and it's repeated. And so I get c1 e to the minus 5x. And here's the other e to the minus 5x, but because it's repeated and I want my solutions to be linearly independent, there is a power of x that goes here. Again, this is any time I've got a root that is repeated. All right, in question 3, I've got m squared plus 16 is 0, which says m squared is minus 16, or m is plus or minus 4i. So here I get two complex roots. And in general, whenever we have complex roots, they are of the form a plus or minus bi. So our solution in that case is e to the ax, so it's e to the real part, plus a combination of cosine and sine for the imaginary b part. And so in our case, I get 0 plus or minus 4i. Well, e to the 0 is 1, and so I just get c1 cosine 4x plus c2 sine of 4x. All right, in question 4. Question 4, I form my quadratic equation m squared minus 8m plus 17 is 0. This is not factorable, so I use the quadratic formula, minus 1 times b plus or minus b squared minus 4 times a times c. And so cleaning all that up, I get 8 plus or minus 4i over 2, which you can reduce to 4 plus or minus 2i. So the 4 is the exponent on the e, and the 2 then becomes cosine 2x and a sine of 2x. Question 3. question 3, the same situation applies to higher orders. So here I have m cubed minus 4m squared minus 5m is 0. So I can factor out this common m, and then the part that's left, factor it, and so I get 3 distinct real roots. E to the 0 is 1, so that's where that is, C1 e to the 0. C2 e to the minus x, and a C3 e to the 5x. Alright, in this question we have m squared plus 9 equals 0. That gives me m is plus or minus 3i. And so I get y of x is c1 cosine 3x plus c2 sine of 3x. We calculate the derivative of that because I have two initial conditions. Y at 0 is 5 and y prime at 0 is minus 3. So plugging all that in, getting C1 and C2, I get my solution is 5 cosine 3x minus sine of 3x. Alright, in question 7. So we see here m squared plus m plus 6 is 0. Alright, which gives us a nasty looking problem. So I've got minus 1 plus or minus. I get an I here from this part over 2. And so I get a rather ugly looking solution. But y at 0 is 0. And when I plug all that in, I see C1 is 0. Alright, so using that fact, that piece is gone. Here's my y of x now. I calculate y prime, which is a product rule. Again, rather ugly and messy looking. But y prime at 0 is 0. And so what I get is C2 is 0, which gives me that my solution is y of x is equal to 0. And looking at my last problem, they're giving us the solution, and they're saying, well, which differential equation did it come from? Well, one thing to notice is that it's oscillating, and the amplitudes are decreasing. So that's really e to a minus ax. So my general solution needs to look like this. And so now that we know what the solution must look like, let's look at these equations. Well, looking at the bottom one here, I get m squared plus 9 is 0, which will be m is plus or minus 3i, so no decreasing exponential. This one has two distinct real roots, so no. This one has m squared plus 1 is 0, so again only a imaginary part, no decreasing exponential. This piece has again two distinct real. This one is m squared plus 2m plus 1 is 0. So it's a repeated root. And so the only one left is this one. And if you check m squared plus 2m plus 2 equals 0, you will see that the roots are repeated, are not repeated, but they are complex. And you will get a decreasing exponential for the amplitude.